I'm Sean Thiel, and in today's presentation, I'll briefly walk through the modeling, simulation, and material selection process for an artificial blood vessel design. During the walkthrough, I will highlight why the recommended material was the most appropriate option in terms of safety and cost effectiveness. So, for the project purpose, the idea behind the project is to replicate the function of a real blood vessel well enough so that it can safely repair a damaged portion of an artery. The successful vessel must be able to maintain blood pressure and blood flow and resist degradation over the long term. And most importantly, it must be biocompatible for the human body. I'll be evaluating the blood vessel under two main conditions: normal flow and worst case scenario flow, to ensure that it's reliable under multiple stress conditions. So, quick walkthrough for the history. Artificial grafts were first developed in the early 1950s. On the left, you can see a picture of Arthur Blakemore and Arthur Voorhees. They did very early synthetic graft work, and they were some of the first successful ones create artificial blood vessels on human patients. Throughout the decades, many materials have been tested for artificial grafts, and over time, they've been refined for constraints such as flexibility, durability, strength, and biocompatibility. That's one of the challenges. We have to make sure we maintain all those factors, all while making sure that the material that we select is cost effective. So for the vessel geometry, all the dimensions chosen were based on the common femoral artery, more importantly for an adult male. So you see the inner diameter of the artery was 10 millimeters, and the wall thickness of it was 1 millimeter. And these values were based off of the adult male, as is the normal flow rate of 350 milliliters a minute. The worst case scenario flow rate is 5 times the normal flow rate. And then the outlet pressure chosen was 107.7 millimeters of mercury, which is about 14.4 kPa. So for the SolidWorks models, 3 vessel lengths will be modeled: 1 millimeter, 10 millimeter, and 100 millimeter lengths. For each model, there will be the same boundary conditions of the volume flow inlet, of the volume flow rate from earlier, 350 milliliters per minute, and the pressure outlet of the 14.4 kPa. And our objective from each model is to find the maximum internal pressure, because that'll allow us to calculate the stress and strain. So starting with the results for the normal flow, you can see the example. This is for the 10 millimeter ones that'll be shown for both of them, but you can expect very similar results from both the 1 millimeter and 100 millimeter models. So the maximum pressures between all 3 lengths were between about 14.36 kPa and 14.37 kPa. And you can see the length of the vessel has very minimal effect on the internal pressure of the blood vessel. Similarly, for the worst case scenario, you can see about 14.38 kPa to about 14.4 kPa across all the lengths. So only a very slight increase from the normal flow. And yeah, even still, the 5 times flow rate from the worst case scenario produces a very minimal increase in internal pressure. So one of the stresses we can calculate for is hoof stress, due to the vessel acting essentially as a thin wall pressure vessel. We can calculate for this hoof stress, which the formula is just simply the internal pressure multiplied by the radius of the vessel divided by the thickness of the vessel. And you can see one of the example equations. This one was for the expanded polytetrafluoroethylene. It's got the internal pressure, which is very similar for all of them, and then the static variables, which are the radius and thickness. That'll obviously be the same for every single one, and they all get around that exact same pressure of around 72 kPa. with very slight deviation. And this is far below the deformation points of all materials, which are in the multiple hundreds of megapascals. So there's absolutely no worry there at all. So while the hoop stress is very similar for all the materials, the strain will vary a little bit because the strain is actually dependent on material properties, most notably the elastic modulus of the material. For the elastic polytetrafluoroethylene, the elastic modulus is highest, around 500 megapascals, followed by the polyurethane, which is around 24.1 megapascals, and then lastly, silicon elastomer, which is about 3.8 megapascals. So when we solve for the strain, which is simply the stress that we calculated before divided by the elastic modulus, we get these strain values, with the EPTFE being the lowest, followed by polyurethane, and then finally silicon elastomer. And all these strain values are all safe. They're far below factors of safety. And yeah, you can strain is a ratio of the change in deformation divided by the initial length. So these are all percentages, with EPTFE being around 0.014%, and then polyurethane being about 0.3%, and silicon elastomer being 1.9%. So since the material properties didn't really help us in the material selection, since every single material was well safe, we kind of move on to the cost analysis. Starting with EPTFE is very, very expensive, around $1,375 to $2,500 a meter, depending on the vendor. This is multiple magnitudes over the silicon elastomer and polyurethane, which are around $6 a meter and $2.3 a meter, respectively. So the cost instantly eliminates the polytetrafluoroethylene. Despite having slightly higher strength and other material properties, it's absolutely not worth the multiple magnitudes higher cost. So that just leaves us with the silicon elastomer and polyurethane. And between the two, polyurethane sticks it out. It's already the in-between in terms of material properties. So it has better material properties than the silicon elastomer. So it's the best balance of material strength, vessel sustainability, and most importantly, hemo capability, which is essentially that material's capability to protect against things like blood clots, thrombosis. So that really helps in the long term of that vessel sustainability. So, quick summary. Those SolidWorks simulations that we modeled show low stress on the vessel in all conditions, showing that each material is entirely viable for the artificial vessel sustainability. And similarly, all the materials produce incredibly low strain values. So that just leaves cost to be the deciding factor, which we decided for polyurethane to be the best selected material for the vessel construction based on the requirements we have. So thank you, and enjoy the blood vessels.